In this video, I'll go over electronic configuration, hybridization, and molecular geometry. Electronic configuration is the distribution of electrons in an atom. Every atom has a nucleus. Electrons, they orbit around the nucleus in shells. In these shells, they contain orbitals, the s, the p, and the d, and the f. Normally, we label the shells from n equal to 1 to n equal to 7, or from k shell to q shell. The s orbital is a circular shape. The p orbital is a lobe shape. The s orbital has a capacity of 2 electrons, and the way you fill the 2 electrons, always make sure that you fill them according to Pauli exclusion principle. This means that when you fit the 2 electrons in the same subshell, you want to make sure that they are opposite spins. You cannot place them both pointing up or both pointing down. So you have to pay attention to that because they are going to repel each other. With respect to the p subshell, it has a maximum of 6 electrons in there. And of course, it's divided into 3 subshells, the px, the py, and the pz. Whenever you want to fill the p subshells, make sure to fill all the subshells at the same time. This means that do not pair the subshells before filling the rest. Let's say, for example, if you have a P4, then in this case, we're going to start by filling 1 electron in each subshell, and then we're going to fill the 4th one. Okay? Do not fill one subshell to the max and then go to the other, because this is not right, because you will be leaving one subshell empty. This is not going to be right in there. P exists in 3 different forms. It's a px, py, and pz. Now, normally the s subshell, we use it in order to make the sigma bonds. The px, we use it also to make sigma bonds, but the py and the pz, we use those to make the pi bonds. The d orbital is made up of 5 subshells and 10 electrons. And the f orbital is made up of 7 subshells and 14 electrons max. The way that you arrange the orbitals is the following in there, starting from n equal to 1, which is the k shell. N equal to 1 has only one s orbital. And going all the way to n equal to 7, which is the q shell. And there. Then in between, you have n equal to 2, n equal to 3. Notice that n equal to 3 has the s, the p, and the d orbitals. N equal to 4, n equal to 5, and n equal to 6. The 4 and the 5 has all the orbitals, the s, the p, the d, and the f. And then n equal to 7 ends up in only the p orbital, no d in there. The way that you arrange these orbitals when you want to write them down, you start with the 1s, and then the 2s, and then the 2p, 3s. This is the order. Then 3p, 4s, then 4p or 3d, 4p, 5s, then 4d, 5p, 6s. This is the order. And then as you go, the f, the d, the p, and the s, and you end up your electronic configuration in 7p. Let's have an example. Write the electronic configuration of carbon. You always use the atomic number, which is the lowest number for the atom in the periodic table, in order to represent the electrons. And of course, the electrons that belong to the outermost shell, these are representing the valence electrons of the atom. So carbon is 6, K shell is completely filled, which is the shell closest to the nucleus. So closest to the nucleus, I have 1s1, 1s2, which is 2 electrons in there. This is hard. It's very hard to lose those electrons because they are very close to the nucleus. And then after 1s1 or 1s2, you have your n equal to 2 shell, and the n equal to 2 shell contains the s and the p. If you fill them up to the 6, then you're going to end up having 4 electrons in there. This is in the outermost shell, which is relevant to the group number of carbon. Same thing for aluminum. In there, it has the K shell completely filled, the L shell completely filled. The M now is going to be the outermost shell. This is where you lose your electrons from this shell over here. This is N equal to 3 shell because you have the N there. This is the 3, and then you have 3 electrons in it. So if, let's say, for example, if aluminum loses the 3 electrons, Al3 plus, then the loss of the electrons, they have to come from N equal to 3 shell. They cannot come from N equal to 2 shell because this is closer to the nucleus. You can either represent it as 2p6 and then stop because you lost the electrons in the S and the P, or you can go ahead and write 3 as 0, 3p0, so that you know that the electrons lost are from N equal to 3 shell. Now, with respect to the noble gases, they are known for their filled outermost shell. So they have the K shell completely filled. They have the L shell completely filled as well. Ions and atoms that have the electronic configuration similar to the electronic configuration of noble gases, these we call them isoelectronic. So let's say F minus, neon, Al3 plus, all of those they end in 2p6. So this is why we call them isoelectronic with neon. Now, whenever you want to fill your orbitals, you always want to fill the s orbital first within the same subshell. Okay, so within n equal to 2 or n equal to 3, you fill the s orbital first, and then the p, and then the d, and then the f. When you're working with the transition elements, let's have an example of iron 26. For transition elements in there, please pay attention that you empty always the outermost s orbital. So here the outermost s orbital is n equal to 4. This is the outermost n orbital, because what you have here for iron, you have n equal to 1, which contains the K shell, and then you have the n equal to 2, which is completely filled. So these two are completely filled. We don't have to worry about them. And then we have n equal to 3. Notice that n equal to 3 here contains the 3s2, 3p6, and the 3d6. But before the 3d6, we have for the 4s2. So what we do with the transition elements only, we do a simple rearrangement, and we accumulate all the n equal to 3 on one side, and we leave the n equal to 4. So this here is going to be the n equal to 3 level subshell. So in order to make the transition elements more stable, we empty n equal to 4. So always empty the s orbital to fill the d orbital. So now your d orbital will be 8 electrons. And the s orbital here for the n equal to 4 will be 0. You don't have to write it down, but it's there. Types of bonds, we have two types of bonds. We have a sigma bond and we have a pi bond. The sigma bond is the overlap of two s orbitals, and the s orbitals, they are circular in shape. A simple example is a hydrogen atom. So I know that every hydrogen has one electron, right? So when these electrons are shared, when you share the electron, this means an arrow from this electrons goes this way, another arrow goes this way. So these two electrons meet. We call the process sharing of electrons to make what? To make a sigma bond. The sigma bond is going to be our covalent bond in this case. The arrow that I just drew is the transfer of one electron. If you wish to transfer 2 electrons, and we will talk about this in details later on, then we're going to use a full head arrow. So a full head arrow, this is a transfer of 2 electrons. A half head arrow is a transfer of just 1 electron. With these types of bonds, I'm not transferring, I am actually sharing these 2 electrons together to make a sigma bond, and with this process, I form a covalent bond. So to make a sigma bond, you can overlap 2 s orbitals together, make them in their bonding state, and make the sigma bond. Now, the s orbital, we know that the s orbital has 1 electron, right? Because hydrogen is 1s1, hydrogen is 1s1. So these 2 electrons, they overlap with each other. Another method of making a sigma bond, is simply by bonding a carbon with a hydrogen. And carbons in there, we're going to use the px of the carbon. So the p orbital of the carbon that lies on the x-axis in there. And precisely, let me go up there just to show you where the px is. When we were laying out the px's and the py's and the pz, this is the px. We said that the p is made up of 3 subshells in there. So the px is the one that lies on the x-axis, and it's this one that we're going to use to make a sigma bond when we overlap it with the s orbital of the hydrogen. So when this overlaps with the circular s orbital of the hydrogen in there, the hydrogen has an electron, the p orbital has an electron, these two, they overlap with each other, and they're going to make a sigma bond in there. Or if I have 2 carbons next to each other, so each carbon will have its px, and the px has 1 electron, so 1 electron from here, 1 electron from there, they overlap with each other and make a sigma bond. With respect to the pi bond, we overlap 2 py's or 2 pz's together. So when you overlap 2 py's together, and of course the pi bond exists between 2 carbons in there. So if the 2 carbons have both py's and the py's they overlap with each other, then in this case they're going to make the pi bond. And the pi bond is represented by a double bond. So you will have a double bond between the carbons. Make sure that every carbon has 4 bonds in there. And so you can have a pi bond, which is an overlap between 2 py's in there. This is a py, this is a py. Or you can have an overlap between 2 pz's as well. So this is a pz. Pz lies on the z-axis. And when the pz's overlap with each other, they also form a pi bond as well. So why carbon has 4 bonds? In order to do this, we're going to work with the hybridization of the carbon. So hybridization explains why atoms like carbon, nitrogen, oxygen form the bonds that they form. So why carbon forms 4 bonds? Why nitrogen makes 3 bonds? Why oxygen makes 2 bonds in there? So this is the explanation that normally is carried by hybridization. So let's start with carbon. Why carbon make 4 bonds in there? To explain hybridization, you have to look at the electronic configuration of the carbon. Because when we work with hybridization, we are always interested in the central atom. Okay, so hybridization is for the central atom in there. So the central atom is going to tell me how many bonds should it make based on the groups that it is bonded to. So here carbon is bonded to how many hydrogens? Carbon is bonded to 4 hydrogens in there. Okay, so carbon here needs 4 groups around it. It needs 4 groups around it. So by looking at the electronic configuration, the K shell is completely filled. So I don't have to worry about shells that are completely filled. So I'm just going to set n equal to 1 aside and look at n equal to 2. The n equal to 2 is the L shell. This is the shell that is going to be responsible for hybridization. So this shell is made up of 2 electrons on the S and 2 electrons on the P. The way that it is written right now, this is how you write it. So you fill normally, or you write the S shell first, because it is lower in energy, and then you go to the P shell, which is higher in energy, for the n equal to 2. So here, these are for the n equal to 2. We said K shell, we're just going to neglect that. The S shell has 2 electrons, so you go ahead and you fill those 2 electrons here. The P shell has 2 electrons, so you go ahead and you fill the 2 electrons in there. Right now, the way that it is written, carbon only is making 2 bonds. Okay? But in reality, carbon makes 4 bonds. So I want to explain why carbon is making 4 bonds. And notice that all the bonds that carbon is making, they are the same. They are not different, they are the same. So there have to be an explanation in there. And the explanation is as follows. 1 electron from the lower energy s orbital will get excited. Excited is a process where an electron from a lower energy goes to a higher energy in there. And when this does, every orbital will have an electron. But still, this is not enough, because if I leave it like this, the bond that is formed from the s orbital is going to be different than the bonds that are formed from the p orbital. And as I'm looking here, all the bonds are going to be the same size, the same length, everything is the same. So what's going to happen here is a process called hybridization. Hybridization is when you merge or combine the s orbitals and the p orbitals together based on how many groups you need around the carbon. So notice here, this carbon that I have here needs 4 groups around it, right? So this means that I want 4 orbitals of the carbon. So I'm going to combine the S and the 3 P's. And this is why I would say that the hybridization of this carbon here is going to be an sp3. Now, when you're combining an s orbital and a p orbital, of course, the shape of the hybrid is going to change, because the s orbital is a circular shape, the p orbital is a lobe shape. If you combine them, this is what the hybrid orbital is going to look like. So the upper lobe is going to be like fat, and the lower lobe is going to be very skinny. Okay? So as I'm looking at the CH4, this explains why carbon is making 4 bonds, because I am using the hybrid orbitals. I'm combining the s orbital and the 3 p's of the carbon in order to make these 4 bonds in there. So CH4 has how many sigma bonds? It has 1, 2, 3, and 4 sigma bonds. And of course, all of these sigma bonds are going to be an overlap between the sp3 hybrid orbital of the carbon and the s orbital of the hydrogen. There is a method in order to draw the hybrid orbitals of the molecule, and that method is called the valence bond representation. We're going to do it just for hydrocarbons, and we're going to do it for single bonds, double bonds, and the triple bonds. So you are only responsible for just single, double, and the triple bonds in there. There's also a sheet, a practice sheet that I posted on eCampus that has more problems on drawing the valence bond representation. So you need to show the overlap of the s orbitals and the p orbitals to show the sigma bond in this case. So for the CH4, we know already that the hybridization, the first thing that you do is find the hybridization of the central atom. And the hybridization is sp3. I already know what's the shape of the sp3, right? It's this shape. This is the shape of the sp3 in there. So around the carbon, I have 4 sp3s. You go ahead and you draw them. So you draw the 4 sp3s in there. These are the 4 sp3s that you are going to draw. And these sp3s are going to overlap with the sigma bond of the hydrogen. We have 4 hydrogens in there. So you have a hydrogen, second, third, and fourth. And each of these hydrogens have an electron. So an electron from the sp3 will overlap with an electron from the hydrogen. Now, notice that every sp3 orbital has an electron, right? And every s orbital of the hydrogen has an electron. So these 2 electrons are going to overlap with each other. And when you have an overlap here, this means that you are going to make a sigma bond. So this is the valence bond representation of CH4. Let's have another example in there. Water. Find the hybridization. As I said, whenever I ask you about the hybridization, hybridization is only for the central atom. So you look at the central atom in there, which is the oxygen. And this is how you do it in a fast way. You look at the group number. So by definition, if you have a central atom that is connected to 2 groups, then the hybridization is going to be an sp, because you only need 2 orbitals. If you have the central atom connected to 3 groups, then the hybridization is going to be an sp2. And then if the central atom is connected to 4 groups, then the hybridization is going to be an sp3. 3. Lone pairs are considered to be a group. So here the oxygen is made up of how many groups? It's made up here of 2 bonds and 2 lone pairs. So this is a total of 4 groups in there. So 4 groups means that I need to use 4 orbitals, an s orbital and a 3p. So this is why the hybridization is an sp3 in this case. To draw it, I know that oxygen has around it 4 sp3s. So you go ahead and you draw the 4 sp3s in there. So I do have my, let me shade this. This is my first sp3. This is my second. This is my third. And that is my fourth in there. All of these are my 4 sp3. Now, 2 of them are bonded with the s orbital of the hydrogen. So you go ahead and you put that. When they overlap with each other, they make sigma bonds. And the other 2 sp3 hybrid orbitals, this is where the lone pairs reside. Okay. Another example, AlCl3. Now, for those, you don't have to draw the valence bond representation, but you have to show the hybridization of the central atom. So the hybridization of aluminum here has around it 3 groups. So 3 groups means that you need the 3 orbitals, s and 2p, so the hybridization is sp2. Same thing in there. You have 3 groups and a lone pair. A lone pair is considered to be a group. A positive charge is not. So if you have something like this, if you have a CH4 or a CH3 positive, then this is not considered to be a group. So you have a CH3. We know that carbon has a plus charge whenever it has 3 bonds in there. So in this case, carbon will have only 3 groups around it. So if it has 3 groups around it, then the hybridization is going to be S and 2p. So it's going to be sp2 hybridization around that central atom. Let's go ahead and draw the or find the hybridization of C2H4 and to draw its valence bond representation. First, you have to draw the Lewis structure of C2H4. We drew that in an earlier video. And there, find the valence electrons and draw the Lewis structure. Now, once you draw the Lewis structure in there, we know that we have 2 central atoms, and you have to find the hybridization of each of these central atoms. Now, there are 2 ways to do that, hard way and an easy way. The easy way is by simply looking at the carbon and applying the rule that 2 groups is an sp, 3 groups is an sp3 hybridization, or sp2 hybridization, I'm sorry, and 3 groups is an sp3 hybridization, and 4 groups is an sp3 hybridization. So here I do have how many groups around the carbon? I have group, I have a second, and all of this is considered to be a group. Okay, so around this carbon here. So this carbon has to be an sp2 hybridization. We're going to do exactly the same for the other carbon. And for the other carbon, we have, let me take those out. Okay, so for the other carbon, it has a group, a second, and the whole thing. So this is again 3 groups around this carbon here. So it is an sp2 hybridization. If we want to go into details in there, you're going to go ahead and draw the electronic configuration of carbon and look at the L shell as we did before. And do the excitation. Here I already did the excitation. Okay, so I already did the excitation from the S to the P, and I ended up having this orbital there. Now, to figure out the hybridization, you have to be consistent with the number of the groups around the carbon. So this carbon needs only 3 groups around it. 1, 2, and 3. I don't care about the double bond. Double bond is still 1 group. So I only need the 3 groups here. So this means that I only need to hybridize the 3 orbitals. See that py orbital that is left? So this p orbital that is left, it's either py or pz. So this p orbital, py that is left, or pz, it doesn't matter. Okay, so this py or pz orbital that is left is going to stay p orbital. It's not going to be hybridized. What's going to be hybridized is the s and the two p's. So in each of the s and the two p's, you're going to end up having an electron, and you're going to end up having an electron in the 1p orbital for this carbon and for the other carbon. It's those two electrons that belong to the p orbital that they're going to overlap to make the pi bond. So in this case, if I want to count the number of sigma bonds, I have 1, 2, 3, 4, and this is a sigma bond because this is an overlap of two px's of the carbons, as we mentioned earlier. So you have 5 sigma bonds, and then this bond over here is going to be a pi bond. Let's go ahead and draw the valence bond representation. So when you draw the valence bond representation there, let's go ahead and relate to the structure. So you do have a carbon. That carbon in here is an sp2 hybridization. So you have 3 sp2 orbitals around it. So this is an sp2 here, this is an sp2 here, and this is an sp2 there. Let's go ahead and write the electrons in this sp2. So this is an sp2 having 1 electron. And this carbon here has another sp2 in there that has another electron. So this is the carbon sp2, and this is the carbon sp2. They overlap with each other and make the sigma bond. Of course, I am using the x-axis in there, and this is why they make the sigma bond. Okay. The ones here, the carbon sp2s, they overlap with the hydrogens and they make sigma bonds as well. And these also make sigma bonds as well. When we draw the valence bond representation, we separate the sigma from the pi. It's easier to view the diagram of the valence bond. So we draw the sigma alone and then we draw the pi alone. So for the pi, it's either the py or the pz. This is the remaining orbital, the remaining p orbital that each have 1 electron for every carbon. Those two, they're going to overlap with each other and they are going to make a pi bond. Another example for the triple bond. Triple bonds, each carbon is connected to 2 groups. So this carbon is connected to 2 groups here. So this is why the hybridization is an sp. And this carbon here is connected also to 2 groups. This is a group 1 and this is a group 2 there. So this is why it is an sp hybridization. We can also prove it by this method by exciting the electron. So here it's already excited, but now I need to hybridize only 2 orbitals. So 2 p's will be left, and those py and pz that are going to be left, those are going to go ahead and overlap with the py and the pz of the adjacent carbon. So each one of these carbons has py and pz. They will overlap with each other and make pi bonds. So we're going to end up having 2 pi bonds in this case. So the triple bond is made up of a sigma bond and 2 pi bonds. The first bond here is a sigma bond, which is the overlap of the hybrid orbitals sp, hybrid orbitals, and then you will have a pi bond here, and then you will have another pi bond there. Those pi bonds are going to be an overlap of 2 py's to make 1 pi bond and 2 pz's to make the second pi bond in there. Okay, so let's go ahead and draw the VBR representation, starting with the sp. You have an overlap between the hybrid sp and the s. This is a sigma, 2 sps from the carbons to make another sigma, and sp and the hydrogen to make a sigma. For the pi, you have an overlap between the 2 py's and the 2 pz's. There are additional examples in a handout that is posted on eCampus. So there's a handout that looks like that posted on eCampus that has additional problems for the valence bond representation. So please look through that, specifically this problem in here. All solutions are found on eCampus as well. Now, as we move also, let's go ahead and work this problem out, drawing the hybridization of the central atom. So again, when we ask about hybridization, we mean hybridization of the central atom. And if there's a carbon, we mean the hybridization of every single carbon. So if I'm looking at the hybridization of this oxygen, you guys, you cannot draw the hybridization before making sure that you draw the appropriate Lewis structure. So I know that when oxygen has a three bonds, it needs to have a lone pair. So you would need to add the two lone pairs in there. Please pay attention to that. So now the oxygen has how many groups around it? It has actually a group, two, three, and the lone pair is four. So this is four groups in there. So this means it needs four orbitals. The hybridization is sp3. For this structure here, let's do the hybridization of this carbon. It's positive charge, and I know that carbon to be positive, it needs to have three bonds around it. So I need only three groups. So the hybridization is going to be for this one an sp2. Now coming to this carbon here, how many groups does it have around it? See, it has three hydrogens and the group here. Do you see it? So three hydrogens and the group there. So this is a total of four groups around this carbon. So the hybridization for this one is going to be an sp2 sp3 hybridization. I'm sorry. With respect to this carbon here, again, it has three groups and another group around it, because if I want to simplify that, that will be three hydrogens, and then that is connected to the carbon with the plus charge here. You see, so this carbon is made up of three groups around it and a fourth group. So the hybridization of this one is going to be an sp3 as well, and this one is going to be an sp3 as well. Always count the hydrogens as groups, you guys, okay? So coming to this carbon is made up of two groups around it, one and another two. Triple bond is considered to be a group. So my hybridization here is going to be sp. This one is an sp. There's no hydrogen here. Please take it out. So this one is an sp hybridization. This carbon over here has, let's go ahead and label the bond. It has a group, two, three, and then a hydrogen. This is four groups there. So it's going to be an sp3 hybridization. This one is an sp3 hybridization as well. And this one is an sp3 hybridization as well, because it's made up of three hydrogens and a group here. So this is a total of four groups. Another example is this one. These are the same. So each one of those is an sp3 hybridization. And this one is an sp3 hybridization. Coming to the oxygen, please put the lone pairs. So you have a total of four groups around the oxygen. So you would need four orbitals. It's an sp3. For this one, you have three groups around it. Every time you have a double bond, it's an sp2 hybridization. So it's a group, it's a two, and it's a three. So that is going to be an sp2 hybridization. This carbon is going to be an sp2 hybridization. And this one is going to be an sp3 hybridization. You guys, don't worry about the structures in there, because we're going to go over these structures in details, and I'm going to show you how to draw them in the next topic. For the VASPER model, molecular geometry, molecular shape. The molecular geometry, by definition, is the arrangement of groups around the central atom, and the shape deals with the lone pairs that is present around the central atom, because the lone pairs tend to squish the sigma bonds in there, so it's going to decrease the bond angle of the compound. So to predict the geometry, you have first to calculate the static number, which has this formula: number of atoms bonded to the central plus the lone pair. You will be given the VASPER table, and I'll provide this to you in the exam. There's an exam version for this table that doesn't have examples in it. This is the only one that you are allowed to use in the exam. So you can find this on eCampus, and you can download it on the day of exam, and you can print that and you can use it. So this Vesper table has a static number, lone pair, geometry, and the shape. And as you can see that the shape is going to change based on the lone pairs in there. So the more lone pairs you have, the bond angle is going basically to decrease. So let's say, for example, if we're working with a static number of 3, static number of 3, meaning that I do have three groups around the central atom. So a static number of 3 means that the hybridization is going to be an sp2 hybridization because I have three groups around the central atom. So if I have three groups around the central atom and I have no lone pairs like BH3, for example, in this case, the hydrogens will arrange themselves in a form of trigonal planar. And the bond angle between the hydrogens and the B is going to be 120 degrees. Now, the moment a lone pair is present, see what happens to the bond angle is going to be decreased because these bonds, they're going to be squished. So it's going to decrease the bond angle. Same thing for the tetrahedral geometry. For the tetrahedral geometry, as long as you don't have a lone pair, then the geometry and the shape are going to be the same. We know that a static number of 4 means that you have a hybridization of an sp3 because you have 4 groups around the central atom. A static number of 2, meaning I have 2 groups around the central atom, so it's a hybridization of an sp. So sp normally is accompanied by a bond angle of 180, which is linear. And sp2 is accompanied by a bond angle of 120, which is trigonal planar shape. And then an sp3 is accompanied by a 109.5 bond angle. Now, to represent the tetrahedral geometry, we represent 2 bonds in plane, 1 bond behind, and another one is in front. So the wedge is going to be considered in front, and the dash line is considered to be behind. Now, again, once you increase the number of lone pairs, so as you increase the number of lone pairs, the bond angle in this case is going to start decreasing. So the bond angle is going to be less than 109.5. How less than 109.5? For example, ammonia has 1 lone pair. So the bond angle is going to be 107 degrees. For water, it's going to be 2 lone pairs, so the bond's going to be squished more, so the bond angle is going to be 105 degrees, and so forth. We're going to stop at a static number of 4, so we're only interested in the geometry of linear, trigonal, planar, and tetrahedral that carries the following hybridization. We're not going to go over trigonal, bipyramidal, or anything like that regarding the molecular geometry. So in order to represent 3D structures, and this is how we do because we want to draw the organic structures on paper, and to draw them on paper, you have to draw them in a 3D. 3D means that you have to represent bonds coming out of the plane, which is represented by the wedge line, bonds coming in the plane, which is behind, represented by the dash line, and bonds that are in the plane. So the wedge line out of the plane, the behind line, which is the dash line, and then the bonds that are in plane in there. Normally, when we measure the bond angle, we measure it between the bonds that are in plane. Okay, because it's easier, it's way easier in there. And this is where we get our solid number. And this is why we say that tetrahedrals are always 109.5. This is how you represent the tetrahedral, and you would need to draw it in its molecular shape whenever you want to determine the polarity. We will discuss the polarity once we talk about the different types of bonds in there. When you represent CH4 or when you represent a tetrahedral geometry, as long as you have 2 bonds in plane, 1 bond in front and the other is behind, you can go ahead and draw your structure the way that you want because remember that you can rotate this carbon over here. So by rotation, you can get all of these different conformations there. So it doesn't matter as long as you have two bonds in plane, one bond behind, and the other one is in front. There are multiple examples and additional examples in the problem sets posted on eCampus. So some of those, this is how the question is going to be. You determine the molecular shape, geometry, and hybridization. You cannot do this without drawing the Lewis structure. So first step, draw your Lewis structure in there. After you draw your Lewis structure, go ahead and get your static number from the Lewis structure. It's number of atoms connected to the central, which is a 3, plus the lone pair, which is 1. So the static number is 4, lone pair is 1. Go to the table up there and see what 4, 1 represents. So 4, 1 represents a tetrahedral geometry and a trigonal planar pyramidal shape. The trigonal pyramidal shape is drawn like this. You have to know how to draw it, okay? It needs to have one bond behind, the other one in front, and one in plane. So you go ahead and you draw that. You would need to draw it because drawing it is important to determine the polarity of the molecule that we will discuss later on. There's again a difference between the geometry and the shape. Those are different. The molecular shape depends on the lone pairs. The more lone pairs we have, the more squished are the bonds, so the smaller is the bond angle. Another example, CH3CO and the CH3. We will go over these organic structures, so you don't have to worry about those. But for now, just know that whenever I have a CO, it's a carbon connected to an oxygen in there. And when I have a carbon connected to an oxygen, it won't make sense if I have the carbon connected to an oxygen and another CH3 in there, and then a CH3 here, because this way this carbon will have two bonds. So there is no way I can have a CO like that. So every time you see a CO in organic means a carbon double bond O. And a carbon double bond O has a name which is called a carbonyl. Okay, so the first thing I would do is get the valence electrons, draw the Lewis structure in there, and in order to secure this carbon to have four bonds, it needs to be bonded to the oxygen. Go ahead and put your lone pairs. So let me add the lone pairs in here. Put the lone pairs because your Lewis structure will not be complete if you don't put the lone pairs. Make sure that lone pairs are there. Once you put the lone pairs, then you can go ahead and draw the VASPER model based on the geometry and the shape of each of these carbons in there. So this carbon is made up of four groups. So it's an sp3 hybridization. It's a tetrahedral. So to represent a tetrahedral, this is how I draw it. A tetrahedral needs to have two bonds in plane, one bond in front, and the other one is behind. Honestly, the ones in plane, normally I like to make them the long carbon chain. So this long carbon chain, this is going to be in plane. Let's go ahead and highlight that. This is the long carbon chain, and then one of the hydrogens, just make it in plane. And then another hydrogen make it in front, and then another hydrogen make it behind. To measure the bond angle normally is measured between the two bonds in plane. So this carbon is going to be a tetrahedral. And then I have this carbon to be an sp2 hybridization. So I have to draw it in the form of a trigonal planar at 120 degrees. So all of those carbon CO, CC, and CC needs to be 120 degrees, a trigonal planar. And then the other carbon is going to be an sp3 hybridization as well. Again, two bonds in plane. So this bond is in plane, this bond is in plane, and then one in front and the other one is behind. So if I want to look at the geometry of this carbon over here, is going to be static number of 3, lone pair 0. It's going to be trigonal planar, and shape is also trigonal planar as well. So this is a small table for you guys relating the geometry to the bond angle and the hybridization. And these are the ones that we are interested in and the geometry that we are interested in. More examples to go in there of drawing the Lewis structure. Just one more thing. Whenever you have a triple bond, remember from earlier example, this is a linear molecule. So the C, C, and N have to be 180 degrees in there. And this carbon in particular that we are looking at has two groups around it. It has the nitrogen, it has the CH3. So this is why the hybridization is linear in this case. The presence of the lone pairs next to the nitrogen is important and it completes the Lewis structure. If I want to look at the hybridization of this carbon, again, when we have carbons, we have to figure out the hybridization of each one of them. So the hybridization of this one is made up of 3 hydrogens and the group, so it's going to be an sp3 hybridization. To be 2 groups bonded to the center plus the lone pair, I have 2 lone pairs in there. So it's going to be 4. So when looking at the table, I have to look at steric number 4 and lone pair 2 because I have 2 lone pairs in this case. And that is going to be tetrahedral and the shape is going to be bent. So you have to draw it as bent and the bond angle is going to be around 105 degrees, or you can simply say less than 109.5.